Good morning, students. Myself, Vijay Shankar from AC Department, Chevrolet Engineering College. Today, we are going to discuss about the second topic in the Fourier series. That is properties of Fourier series. We already discussed about some properties, that is the linearity property, time shift property, frequency shift property, and scaling property. We already discussed this linearity, time shift, frequency shift, and scaling property. Now you can see the another property we have here. Another property. That is a time differentiation property. Time differentiation property. Here the statement you can see, if x of t is a Fourier series x of k, then you can prove that the derivative of input function x of t applying the Fourier series will get the jk omega naught x of k. Jk omega naught x of k. Here, to prove this time differentiation, you have to use the exponential Fourier series. That too is a synthesis equation. You know the synthesis equation is x of t is equal to sum of k equal to minus infinite to infinite x of k e power jk omega naught t. So actually analysis equation means x of k is equal to the integral t 1 by t x of t into e power minus jk omega naught t dt in the integral value. Here I am using we are using here a synthesis equation x of t is equal to, okay. So I will explain here this the whiteboard. Let us see here the fifth property, time differentiation. Time differentiation. Okay. So what is the statement saying that x of t, the Fourier series, apply the Fourier series is x of k. Then you have to prove that the d by dt of x of t, the Fourier series is jk omega naught into x of. Okay. So now we go for the proof. To prove the time differentiation property in the Fourier series, use the synthesis equation, that is x of t is equal to sum of k equal to minus infinite to infinite x of k. Here the positive exponential here e power jk omega naught t. Now we can apply the derivative on both sides. D by dt of x of t is equal to the sum of k equal to minus infinite to infinite x of k. Here there is no any t terms here, so it is a totally constant. Now in the exponential only we have the t term. So d by dt of e power minus jk, not the minus, plus jk omega naught t. So what is the derivative of exponential? E power jx means e power jx into one value here. With respect to the x, it is a j. And with respect to the t, we are applying that the t coefficient is a jk omega naught t. So the e power jx k omega naught t, and the t coefficient is a jk omega naught. Jk omega. Therefore, the d by dt of x of t is equal to the sum of k equal to minus infinite to infinite. Now I'm writing these two functions as a one function, jk omega naught into x of k is a single function into e power jk omega naught t. See, observe here the two functions, the two equations. The x of t is sum of k equal to minus infinite to infinite x of t. Means x of t is input function, the time domain function. Applying the Fourier series, we'll get the x of t. Now, the time domain function is the derivative, the d by dt of x of t. What is the frequency function? Jk omega naught t into x of t. After applying the derivative with the for the time domain function x of t, the x of t is multiplied with the jk omega naught t. Therefore, the d by dt of x of t is a Fourier transformation, Fourier series, not the Fourier transformation, sorry. Fourier series pair of jk omega naught x of t. What it matters, students? Is a proof. Okay. By observing these two equations, x of t is here the time domain x of k. When the x of t is a derivative, is multiplied with the jk omega naught t. Got it? So the same thing, the d by dt of x of t. The Fourier series is jk omega naught into x of t. The next one is a convolution in time. The sixth property, convolution in time. It is these all the properties is very important, my dear students. Be careful and listen carefully. If x of t, the Fourier series, the x of k, and the y of t, the Fourier series y of k, then the convolution between x of t and the y of t. The convolution between x of t and y of t means the time is convolution here. The time is convolution. So the x of t with the convolution of y of t, there is a symbol here, the asterisk, we're calling it as. Apply the Fourier series for that function to get the frequency domain is t into x of k y of k. T into x of k y of k. Got it, my students? Now, using this statement, you have to prove the convolution time domain property. Let us see in the whiteboard here. The sixth property, convolution in time. Convolution in time. Time domain. So what is the statement saying that if x of t, the Fourier series is x of k, Fourier series is x of k, and y of t, the Fourier series is y of k, then you can prove that assuming that the z of t is equal to the convolution between of x of t and the y of t is an asterisk, my dear students, y of t. Its Fourier series function is its Fourier series fs is a z of k is equal to you have to prove the t into x of k and the y of k. Okay. I go with the proof. To prove this convolution in time domain, use the analysis equation, not the synthesis equation. We know the analysis equation is z of k is equal to, as I am taking the z function, the integral t, 1 by t here, z of t, e power minus jk omega naught into t dt. So what you have to take the z of t is the z of t is a convolution between the two functions. What is this convolution between the two functions? Z of k is equal to 1 by t, the integral t. Z of t is x of t with the convolution of y of t. And it is e power minus j k omega naught into t dt. What it matters to us. Now, what is the formula for the x of t with the convolution of y of t? The convolution. The formula here, the x of t, the convolution of the y of t is equal to integral minus infinite to infinite, integral minus infinite to infinite, x of tau, this is tau, my dear students, y of t minus tau d tau. Is a formula for the convolution integral. It is only for the continuous time functions only. The discrete time function is the sum of. So replace this x of t, the convolution of y of t as x of tau and y of t minus tau d tau. So 1 by t. Here the one integral is there, that is a time period. Now I am using this the integral minus infinite to infinite. Here the x of tau is there, x of tau, y of t minus tau into d tau. Okay, I replace the convolution function as an integral. And e power minus j k omega naught t dt. What it matters to us. Now, the two integrals we have. The first integral, if I am using the 1 by t into, not the 1 by t, I directly take the minus infinite to infinite. The tau terms in one integral, x of tau and the d tau. For another integral, the 1 by t, is the t, write all the t terms, that is having the t, the y having the t minus tau, and exponential having also e power minus j k omega naught t dt. Okay. So observe here in the second function, so totally the second integral, t minus tau means the time shift property. By using the time shift property, whatever how many number of samples are shifted in the right hand side, the tau samples is multiplied to the x of k or the y of k. Here the y, I use a variable is a y, so you'll get the y of k only. Or otherwise, assume that the t minus tau is equal to tau. T minus tau is equal to m. Let t minus tau is equal to m. Or directly can write by using the second property, time shift property. Or if you are having any confusion, write this t minus tau is equal to m and t is equal to m plus tau, and tau is a constant. So apply the derivative on both sides, dt is equal to dm. So replace these functions. So that is equal to integral minus infinite to infinite x of tau d tau, x of tau d tau, and 1 by t, integral t, y of t minus tau, I assume the m, e power minus j k omega naught, the t now it is a m plus t, m plus tau, not the t, m plus tau, and dt becomes a dm. dt becomes dm. Okay. Now, split this exponential as a two parts. That is equal to, that z of k is equal to, z of k is equal to, there's a continuation here, my dear students, applies the integral minus infinite to infinite, the x of tau d tau, Okay. Now in the second integral, 1 by t integral t y of m. Now the exponential e power minus j k omega naught m function is there. Okay. Another one is a e power minus j k omega naught tau dm. Got it, Madhya? Here the tau term is there. You can bring this in the integral minus infinite to infinite x of tau e power minus j k omega naught tau theta. And the 1 by t here, another integral 1 by t, the integral t, the y of m into e power minus j k omega naught m into dm. See, observe this, the two integrals, both are the same. Here the variable is tau and here the variable is m. It is analysis equation only. But here there is no any t term is there. Even if it is a minus infinite to infinite, or the t is also minus infinite to infinite, 1 by t is not there. So multiply the t and divide the t here. So integral, this limitations is also from t limitations, let us assume. So x of tau e power minus j k omega naught tau d tau. And another integral is 1 by t, the integral t y of m e power minus j k omega naught m into dm. Now both the functions is the same now with the variable of tau and with the variable of m here. That is replaced as the analysis equation. The x of tau here, the x of k, t into x of k. And this function is becomes of y of k. Got it, my students? So finally the z of k is equal to t into x of k and y of k. Okay. That only you have to prove the convolution in time domain. Let us see here. The z of k is equal to t into x of k, y of k. Once again, by using the analysis equation, z of k is equal to 1 by t, the integral t, z of t e power minus j k omega naught t dt. And here you can take the convolution formula, apply, substitute the convolution formula here, and both the integrals are separated. That's tau and the t terms, and t minus tau, or directly we can by using the time shift property, using e power j k omega naught tau into y of k. Z of k is equal to x of tau, and this function is multiplied with e power minus j k omega naught tau into y of k. Simply saying that e power minus j k omega naught tau is multiplied with x of tau and the d tau. This integral becomes of x of k and the y of k. It's a very, very important property in the Fourier series, my students. The same property will get in the Fourier transformation and remaining functions also. The Fourier transform and the Laplace transform and the Z transformation. The later will get the Laplace transformation, Z transformation, and the Fourier transformation also. We'll discuss in that unit. You see, finally we have x of tau, y of t minus tau, d tau. Simplify this function, the t into x of k, y of. Got it? And another property is a multiplication property. The multiplication or modulation theorem also. Multiplication or modulation theorem. See, what is a multiplication? Here the multiplication is the time domain. Previously, we use convolution in time. The product will get in the frequency. You see here, the product x of k and y of k is both are the product. Now I am taking here the input, the time is product, frequency is a convolution. Frequency is convolution. So multiplication property, if x of t the Fourier series x of k and y of t the Fourier series y of k, then z of t, take the product or multiplication of the time domain function x of t and y of t, have to prove that the convolution of both the functions x of t the Fourier series is x of k and y of t the Fourier series y of k, and we'll get the convolution the frequency. Here also you can use the same analysis equation, z of k 1 by t the integral t z of t for minus jk omega naught t dt, and z of t can take as x of t and y of t, and here in this function the x of t is there. Replace this x of t by using our synthesis equation. That synthesis equation is x of t is equal to sum of k equal to minus infinite to infinite x of k e power j k omega naught t. Then you can simplify. The function. We'll get the convolution between. But before that, the index summation is changed as here the k value is there. That k is changed as the m, because whenever it is e power j k omega naught t and e power minus j k omega naught t, both are the same base, and you can add the power, you'll get the e power 0. The e power 0 becomes 1. So we can't derive or we can't do the multiplication or the modulation theorem to get the x of k is the convolution of y of k. For that case, before going to prove the value to the function, you can change the k values as the m values. Okay, I'll explain here. That is the next property. I think this property is seventh property. Multiplication or modulation. Multiplication in time. Okay. So what is the statement saying here? The x of t Fourier series x of k and the y of t the Fourier series y of k, then you can do that z of t can take as a product of the two input functions, the time domain functions x of t and the y of t. Its Fourier series is z of k is equal to convolution of the two frequency functions x of k with the convolution of y of k. Take the proof here. So listen carefully, my dear students. Here I am doing only by taking of exponential Fourier series formulas and substituting the convolution equation or substituting the synthesis equation and simplifying. Simplifying, you'll get the proof of any of the problems. So first of all, I am taking the analysis equation. That analysis equation is z of k is equal to 1 by t, the integral t, z of t, e power minus jk omega naught t into dt. So now replace that z of k is equal to 1 by t, the integral t, z of t. What is the z of t? Here the x of t and the y of t. X of t and y of t is a multiplication of the modulation e power minus jk omega naught t into dt. Got it, my students? Now the x of t, by using the synthesis equation, what is x of t is equal to sum of k equal to minus infinite to infinite x of k into e power plus j k omega naught t Now I'm changing this k as a m variable is equal to the dummy variable if I am taking m is equal to minus infinite to infinite x of m. Wherever the k is there, you can replace the m omega naught t. So you can substitute this x of t by using this function x of t is equal to. Now the z of k becomes z of k is equal to 1 by t, the integral t. What is the x of t now? The sum of k equal to, not the k, m equal to minus infinite to infinite x of m e power j m omega naught t as of x of t. Another function is there, the y of t into e power minus j k omega naught t d. Now we can simplify. So both the exponential basis is same. Add the power. So 1 by t, the integral t. Another one is the sum of m is equal to minus infinite to infinite, or otherwise you can replace this as sum of km is equal to minus infinite to infinite x of m, that the capital letter it is x of m, and now the right the integral value 1 by t integral t y of t, and both the exponential is the same. What is the common term is there? J is a common term and the omega naught t is also common term, omega naught t d. And in between there is a k is there, minus j k omega naught t, and here the plus is there, so we'll use the minus m. Okay, my dear students, that is equal to the sum of m is equal to minus infinite to infinite x of m, and this is a frequency shift property, my dear students. According to the frequency shift property, the frequency is here, of k, and sum of m is equal to minus infinite to infinite. Totally it becomes of y of, by using the frequency shift property, y of, actually it is a k is there, y of k, instead of k here the k minus m, so y of k minus m. The sum of m is equal to minus infinite to infinite x of k, y of n minus k. Here the k minus m, replace the m value as k, and the k value is the n. So to get the convolution sum equation, k is equal to minus infinite to infinite x of k and y of, replace the k as now n minus t, y of n minus k. This is the equation for the convolution sum. So convolution sum between of x of and the y of. Therefore, it becomes of x of k convolution to the y of k. What it matters is a very important that of k is equal to. Only the finally you have to do the x of k with the convolution of y of k. Time domain convolution formula is the difference, and the frequency domain convolution is the difference. Frequency means it is a discrete function. Continuous time function is x of t and y of t convolution. But here the convolution sum is nothing but is a discrete function. It is representing as the sum of k equal to minus infinite to infinite x of k, y of n minus k is a convolution sum equation of x of k with the convolution of y of. Got it, students? Now, so the same the interchanging of summation change of the k variable as m variable. So see, the z of k is equal to sum of m is equal to minus infinity infinite x of m, y of k minus m is the convolution. X of k with the convolution of y of k. Got it, my students? And next property, the eighth property, is Parseval's theorem. Parseval's theorem. If x of t is a periodic power signal, the statement C, my dear students, here. Parseval's theorem. If x of t is a periodic power signal with the Fourier coefficient x of k, see the Parseval's theorem statement saying that the x of t is a periodic power signal with the Fourier coefficient x of k, then the average power in the signal is given by, and the average power P is equal to sum of k equal to minus infinite to infinite, the squared magnitude of x of k, squared magnitude of the frequency function. See, for that function, we are not using the analysis equation, the synthesis equation here. Directly by taking the power signal limit t tends to infinite, 1 by t, the integral minus t by the t by 2 x square of t dt. That x square of t dt is 1 by t as a periodic signal, 1 by t, the integral minus t by the t by 2, the squared magnitude of x of t dt. And this squared magnitude of x of dt, we can write as, see here, x of t, the squared magnitude of x of t, we can write it as x of t. And another one is a complex function, x star of t. Got it, my dear students? Whenever it's the magnitude, squared magnitude of x of t is x of t and x star of t. So see here the 1 by t, the integral minus t by the t by 2, x of t and x star of t dt. By using the analysis equation, by using the synthesis equation, we know the x of t is equal to sum of k equal to minus infinite to infinite x of k e power jk omega naught t, jk omega naught t. Replace here. So I take the x of t is equal to sum of k equal to minus infinite to infinite x of k e power plus, actually here the plus jk omega naught t. And now here the star is their conjugate function, x conjugate of t. Conjugate means the real term is there is no any sign changes occurs, only the imaginary term sign it changes. So the x of k into, now the positive exponential becomes the negative exponential, jk omega naught t. The plus is becomes a minus. Imaginary term coefficient sign is only the change. Okay, and here the star will get the x star also. The total function having the star here, x star, x of t, and here is also the full star. So it becomes of x star of k and e power star is becomes plus as a minus. So substitute this function in the 1 by t, the p is equal to 1 by t, the integral minus t by the t by 2, x of t, and the x star of t can replace as sum of k equal to minus infinite to infinite x star of k e power minus jk omega naught t, and here is a dt is there. Got it? So separate the sum of function, sum of k equal to minus infinite to infinite x star of k, and another function we have, that is 1 by t, the integral minus t by the t by 2, and x of t here, x of t, and exponential function is a negative exponential e power minus jk omega naught t dt. So observe here, there is a total function is the analysis equation only. So sum of k equal to minus infinite to infinite x star of k. This total function is the analysis equation x of k. So now see the x of k and x star of k becomes squared magnitude of x of k, minus infinite to infinite, and the squared magnitude of x of k. As whatever you are saying, the x of t and x star of t, the squared magnitude of x of t. Here also the x of k and x star of k is a squared magnitude of x of k. So the powers of Parseval's theorem P is equal to the sum of k equal to minus infinite to infinite, the squared magnitude of x of k. If x of t is a periodic power signal with the Fourier coefficient of x of k, then the average power of the signal is given by sum of k equal to minus infinite to infinite x of k magnitude, squared magnitude of the x of k. Got it, my dear students? And the last symmetric property here. The symmetry property, if x of t is a real, then x star of k is equal to x of minus k. Is a real means there is no any sign changes here, even if it is a negative k values also. If x of t is imaginary, then x star of k is equal to minus of x of minus k. For the negative values, the sign is becomes a minus here. If x of t is real and even, the imaginary coefficient is a 0. If x of t is a real and odd, then real of x of k is a 0. The real and even imaginary of x of k is 0. If x of t is a real and odd, then real of x of k is a 0. So these are the different types of properties are there in the Fourier series. See, the first property is a linearity property. Second one is a time shift property. Linearity, time shift, then frequency shift and scaling property, 4 properties, and time differentiation and the convolution property, 6 properties. And 7th property is multiplication of the modulation property. And the last but one is Parseval's theorem and the symmetry properties. Totally the 9 properties are there in the Fourier series. We learn, my dear students, it's a very important property. So by using these properties only, you can go through to find the examples of the given graphical representation of the exponential pulse, periodic exponential pulse, and another examples, periodic rectangular wave. Okay.